Hi everyone, today is a new video on the RKALC Learning Center. Um, we are talking about strut and tie modeling. Navigate to RKALC website and go to Learning Center to see the previous videos and featured topics. The previous series of videos included steel warehouse modeling. If you click on the photograph there, you'll find all of the details of the previous example together with screenshots of the calculations we've done together and assumptions, cross checks, the videos, and you'll see as well a PDF, a downloadable file. In this video, we'll be talking about the strut and tie modeling, which is here, already prepared beforehand on the website, so you can read it while on the train or when you have some time. Today's example is a shear wall that is supporting a 20-story building. Sample RKALC plan. We've got the wall is 10 meter long and has a tributary area of 8 by 12 meters. This is the geometry of the wall, 3 meter story to story high, and we'll work through the load calculation. Next page here, we'll see the slab thickness is 220 millimeter. That is accounting for 5.5 kPa, finishes being 1.5. That is typical for residential building in New South Wales generally and Australia. You need to count as well the own weight of the wall, which is considerable for a very high building. Live loads 1.5 if you refer to self-contained dwellings in the Australian standard 1170.1. So the total line on load on the wall is the kPa on the floor times the tributary area times 20 levels divided by the length of the wall. That becomes 2045 kilonewton per linear meter, and add as well the load on weight, so altogether becomes 2500, or if you divide by 20 it becomes 125. So that is the wall geometry. We've got total span 10 meters, columns down under 1200, and center to center becomes 10 minus 1200, and you've got the clear span is 7.8. Usually you go the effective height of the wall, that is D region, essentially is roughly 0.75 or 0.8. Beyond that, the stresses become uniform and the wall lands. Then you get the stresses. Here you've got a lot of tension happening, so you need to work around it. I'll assume in this example that the gravity loads will govern the design, because usually they are highest when it comes to the nodal checks. There will be cases where the wall is governed by earthquake or wind loads, but for walls landing on columns, the lateral system will have a weak link, essentially those two columns, so it won't really work harder on laterals generally, but each case has its own merits. Theory, if I just share with you Schleck, so that is the classical example that presented by Schleck et al. 1988, showing the uniform stresses until you get to the D region, which is Z height, which is the ratio of the span. So that is the theory. And if you're looking at the stress field or the elastic stresses, if you're, for example, you go model this using ETABS or FECALC 3D as well, previous examples talking about FECALC, you can see the stresses in the S11 direction. You've got here like 7 MPa or 8 MPa tension in this direction, and you get the stress concentration when it goes to ST2, the vertical under or over the columns. But those stresses won't hold true because those are elastic, do not account for the cracking in the concrete, which is typically modulus of rupture on tension 0.36 square root of F prime C, and some schools just like limit the tension in concrete to 1 MPa. So the theory, so you got that uniform stress goes all the way down, and then you get the D region, that is roughly 0.8 of the span. If you're not sure, it doesn't matter, because you need to work out this strut angle. Some people say it should be 60, 55, can be 70. That will be to your interpretation of concrete references. I will adopt here 60 degrees or 65 degrees, let's say. So you'll end up with one strut goes all the way down, so that will be CCC node, because you've got compression here, compression there, and between the nodes you've got compression. That will be equivalent to the tie loading here, and those will be two CCT nodes landing on supports. So the elements will be like you've got fan shape strut there, fan shape, and you've got tie and struts down up there. So there is a bit of theory. You can read this one through the Learning Center website, but most important, you need to work out the flow procedure. You start with the building the model, check the angles of the strut. Are they within the allowable angle that you've nominated? You keep iterating until you get that, because the wall has a height of 20 stories. So you need to establish where is the this disturbed region, essentially, or the D region. Then you apply the loads. Try with initial thickness, check nodal stresses. If they are within the limit, you keep going and design the reinforcement. Otherwise, you keep increasing the thickness, or maybe revise the MPa for the concrete. And then we'll show how we'll do that actually in our example. So going to STM calc there, go to wall, and then we just try with the 65 MPa, for example. The wall height is, if we call it 6 meters, the span is 10,000, and start with the 300, for example. You've got 1200. The width of the columns. Now width of support. Now width of applied load actually is width of the wall, and location is center of the wall. So that is the loading, essentially. If that becomes, let's say, 5 meters wide, it goes less. But here, the whole wall is being loaded uniformly. Now we look at the width of the support, 1200, these two columns down there, and then we put the loading, which is 25,000, and the service load becomes 25,000 roughly. To convert it to SLS, you just divide by 1.3 roughly from experience. So that is what you see here. Everything is red. So that is, if you're using like Excel sheets or hand calculations, you start with something, you check the node. If it doesn't pass, then you revise the geometry and keep iterating forever. Here you can just feed those numbers until everything is fine. So here, what I'm gonna do, I'm increase the wall thickness to 350. See what's happening there. The strut angle is 71.1. So it shows being red. So I would reduce, let's say 5,800, and then check. You're still not really good. So it's now reducing to 70.8. So what we can do, so the height of the model is the height between the nodes, essentially, center of nodes. So if we try, let's say, top node 300, so you get, at the bottom node, let's say 250. So the model gets compressed, and that angle here is becoming like within 70. You can nominate any angle that you like for the strut inclination. And now the whole thing looks fine because we kept iterating. Maybe if you wanna, so you look at the reinforcement here is 10,000. That is a lot of reinforcement essentially for this given load. Maybe your aim is to reduce that reinforcement. So how will you do that? Will be essentially increasing the depth of the wall, or playing with the loading. Maybe you want to reduce the live loads because the building has typical height. So looking at this one, everything is working fine. Each node, so if I'm talking about the top node, so top node is divided into left node and right node. So you will find both nodes. So this is a perfectly symmetric model. The stresses within the node, top stress, which is here, is essentially the load divided by the length by the thickness of the wall. And so all of the stresses are within the CCC node allowance, which is 0.9 times 0.65 times F prime C as per the Australian standard at the strut and tie modeling. Now CCT node, you multiply that number by 0.8 because it has a less capacity. So what we've got there is the allowed MPa is 30 for 65 MPa, a concrete, and the applied is 29 on the left node there. Whereas the maximum stress happening is at the bottom, where we are landing on the column. So that is the base stress. Side stress is where you've got the reinforcement is pulling essentially. So that would be the side stress. You just divide the tie load, this one there, by the depth by the thickness. So that is all within. So you can appreciate that the node is not hydrostatic. Hydrostatic nodes are a myth. Some people are a fan of having hydrostatic nodes for some reason, but there is no problem at all having non-hydrostatic node if you understand the principles and you work out the shear using Mohr circle. So now everything is fine. So we're looking at the reinforcement. If you're nominating let's say N32's area of which is 804. So you need to divide this by 804. You come at roughly 13 or 14 bars. But what matters the most is that you need to distribute the reinforcement over the depth of the node there. So when you're looking at the calculation agenda, so you will find how the depth of the node is 500 as per our model, and that's the width of the wall. So you spread the rebar throughout the node, so your calculation hold true. Now we are done with saving the nodes. Now we'll go to struts. So in a strut, click on this one, and you'll see all of the code related items for the strut. So there, what matters the most, if do you need bursting reinforcement or not. Now this number is the total reinforcement. So when you're looking at the calculation agenda there, so that total reinforcement is divided by each face. So you get that one horizontally divided by height of the wall. So you get the spread of reinforcement. So divided by, let's say, 314, the area of N20s. You will require N20 at 222, but we'll provide 200 there. And same approach there, but we are dividing by the span to get the vertical reinforcement coverage. So that will be fine. So that wall is all good. And you can, at the end of the day, ask RKALC assistant opinion of this one. It can help you iterate if you wish, but it is a simple matter there. And when you're clicking on my wall, or sorry, calculation, it will generate, the software generate a report. Again, if you're going to RKALC Learning Center, you will find all of this information available to you together with this videos being recorded at the moment. Thank you very much.